Okay guys, how's it going? We're going to finish off the kinetics chapter with 3 problems, all relating to mechanisms and how we determine them. We're going to end off the whole thing. We'll top it off with some catalysts and how to determine what's an intermediate and what is a catalyst in a reaction. And hopefully that'll cap off the chapter and you'll be prepared and ready to go into that exam. So let's get started. Given the following proposed mechanism, predict the rate law for the overall reaction. We're given an overall reaction, as we see, and an established mechanism. When we look at a mechanism, we need to look at a couple things, and in particular, we're looking at whenever on the sides and the margins here, if it's a fast or if it's considered a slow step. Now, you've probably heard this before, but the slow step is the rate determining step. So let me fix that. Is the rate determining step. And what do I mean by that? Well, I mean the slow step is going to be the driving factor for what causes your reaction. Like, how do we quantify and how do we characterize how fast the reaction is going to go? Well, the slow step is going to be the limiting factor in this process. So by all intents and purposes, we can consider that to actually be the rate law. So what we have here in a mechanism is 2 different reactions here. And what we call these 2 different reactions, we call them elementary reactions. Elementary reactions. Now, an elementary reaction, if it's the slow step, and if it agrees with the established overall reaction, and through experimental data, then we can say that that elementary step, if it's the slow step, will be our rate law. Now, what do I mean by that? I mean that because the slow step is the first step in this particular reaction, we can then say that that elementary reaction with all of its coefficients will be the rate law for this reaction. So let's take a look. So we have this first bit, the NO2 plus Cl2. It gives us NO2Cl plus Cl. Okay, there are coefficients of 1 in front of the NO2 and the Cl2, so I'm going to write them in just for clarification. The coefficients of an elementary reaction, if it's the slow step, become the orders for the rate law. And I'll repeat that. So remember that a rate law, so the rate law, what I mean by that is this particular rate law, because it agrees with, and it's the first step and it's the slow step, we'll have a K constant, obviously, and then we'll have NO2 to some M and Cl2 to some N power. We did in the very beginning of this whole chapter, we talked about orders, the orders of each reaction. Is it a first order, is it second order, and so on. We did the method of initial rates and we figured these out. But we have an alternative method to do that now, and that's if we're given the elementary reactions. The coefficients of the elementary reactions, i.e. the ones that we see here, become the M and the N respectively. So my rate law for this reaction will be NO2 and Cl2. So which of these examples agree with that? This is a really easy example, obviously. I'm picking one like this just so we can show the steps. And that would be, it looks like it's going to be A in this case. NO2 Cl2. Great. So that's going to be our answer for this one. Let's move on to something that's a little more difficult. Now, let's figure this out. So in 25, we're giving another reaction. And we're given the fact that the slow step, which I said we should be looking for, is in the second step. Now let's identify some really key features of a mechanism. So we have this forward and backwards arrow in 2A. We have A plus B, another forward arrow, and AB. Okay, so when we see that, if you recall, in lecture or in Chemistry 101 for that matter, when you're given a set of equations like this, similar to Hess's law in thermodynamics, you can cancel reactants and products found on the opposite side of arrows. So what happens here is that really this equation would, whenever we are crossing out things found on both sides, this A, for example, We call those reaction intermediates. Intermediates. And those are little bits that, remember when we talked about the energy diagrams, we said that when we have two humps, this little intermediary product that we see here would be the bit that doesn't actually exist at the end of the reaction, but it is a stepping stone to the next, to produce the second step of the reaction. So that's what I mean by intermediate. So, okay, what do we do with these intermediates? Well, intermediates do not appear at the end of the reaction. So that means then that when we do our overall equation, we should not see any A's in it. And that agrees with what we see here at the top. There's A sub 2's and there's B's, but there are no A's found in the equation, which is why they're going to be considered intermediates. Okay, so normally, if this was the slow step in the first step, we would be done, and my rate law would just be D, K, and A2 to the first power. But because my slow step is in the second step, we see that my rate law should be A to the 1 and B to the 1 because there's a coefficient of 1 on each of these. However, that does not agree with our overall equation because our overall reaction does not have any A's or standalone A's in it. So my mechanism cannot rely on this intermediate that we see here, meaning that this guy right here is messing everything up, this A. So what we need to do is write this A in terms of other reactants that we have in this reaction. And in particular, we can look up to this equation up at the top here. Now I'm going to write it down again down here. So then A squared and 2A. Okay, well let's imagine this. The rate law is equal to K1 and A2. I'm just saying what this would equal to if this was let's say the first equation we actually composed a rate law for it. This is what we would write. That rate is equal to K1 and A sub 2. And since the reverse reaction is the same, it would be that K1, I'm just going to, instead of doing K1, I'm going to do K inverse because it's going the opposite direction, is going to be equal to A squared. Now hopefully that makes sense. All I'm doing is writing what the rate law would be if we just simply considered there's just the top equation. Now if I wanted to solve for just one of these A's, I would have to get, well, first things first, I'm going to divide this K over to the other side. And what I can do then is, once these cancel, is if I want to solve for just one A, because the whole idea of what I'm doing right now is that I want to replace this A that's in the intermediate spot up here with something else, because the A is an intermediate and I don't want it in my overall reaction because it wouldn't reflect what's actually true. The overall reaction at the end does not have that A, so we need to replace it with something else. And what I'm doing when I get the square root of both sides, I see that I get this new equation, which is K1 inverse, and A2, and I'm getting the square root of it. Remember that when you get the square root of something, you're really raising it to the 1/2 power. And that's equal to A. Okay. Let's please hope that makes some sense. Because for a lot of people, that's a little bit of a stretch, but I want you to remember that all you're doing is solving for X. Really, that's just an algebra question. How do I solve for I'm really just doing a substitution. I want something to substitute for this A, so I look at the top equation and I see that I can replace A with the square root of A over A sub 2. That's all I'm doing. I'm just solving for A like that. So then let me get rid of this little part right here, because all I really care about is this, which is it's important right now. Okay, so now let's go back to this second part of this equation. Well, the rate law for this second equation here should be rate is equal to, let's see, so it's going to be K2 because it's my second equation. It's going to be A and then B. And they each have a coefficient of 1, so it's going to be 1 and 1. Now, because I just made a substitution A, I can substitute this whole bit here into the part here for A, which is exactly what I'm going to do. So then I get this new equation, which is rate is equal to K2, and I get K1 inverse, and I get this A2 to the 1/2 power. And then I still have that B hanging out here. Okay, so let's worry about something really quick. All of these K's are just kind of arbitrary constants, so I'm just going to combine them all into one big K, because they're all just arbitrary constants, so it doesn't really matter. They're all dependent on temperature, so we don't really care. Okay, so my overall reaction at the end, my rate law at the end, is rate is equal to big K, and that's going to be A sub 2 to the 1/2 power and B. Okay, now it looks like, given that, my answer is going to be, let's see where we're at, it's going to be E in this equation. A sub 2 to the 1/2 and B. Remember, let's look at what we did. We looked at the mechanism and we saw that the slow step was in the second step, which is perfectly fine. However, a reaction intermediate, A, was found in the slow step, and I cannot be okay with the reaction intermediate being in my rate law. So instead, we used the first equation, this bit up here, and we made a substitution. We said, how can I rewrite A as something else? And I did that by getting the square root of both sides, and I was able to get to the 1/2 power of A sub 2. Then, when I wrote my rate law in again, I replaced this A with what my substitution was before, and I could solve for the new rate law with respect to other variables. Again, this requires some practice. I encourage you to do as many problems as you can with this in the slow step, because this is going to be the one that you see on an exam. It's much more difficult than just simply plugging in the answer, as the first problem I did in this section. So this is going to be the harder version of this, but I 100% believe that you can get this if you practice a little bit more. I hope you can follow along with this. I hope, because this is something that's a little difficult to explain, but once you get it down, it's clear as day how to do these problems. So let's do one more and we'll cap off the kinetics chapter. It's going to be number 75. The mechanism for the destruction of ozone is in the upper atmosphere, is given by these two elementary reactions we see here. Okay, now which species is a catalyst? And which species is an intermediate? Well, an intermediate is something that, well, let's think about what we saw in the previous problem. Well, an intermediate was like A. And if you noticed, A was created and then canceled in the second equation, as we see here. But what about, so which one do we see that was created and then subsequently canceled? Well, we see that this NO2 was created, and I would cancel this NO2 with another one on the other side, so it would be immediately destroyed. So if you create a product and subsequently destroy it in the next step, we call those intermediates. So in this case, NO2 is an intermediate. And how do I differentiate that between a catalyst? Well, a catalyst is something that you start with and then you recreate it later on in the reaction. So, but it will not be a part of your overall reaction. So let me restate that. So a catalyst is present at the beginning and present at the end, but will not be a part of your overall reaction. So let's look for that. So what are the two things that are present in the beginning? Well, I have this O3. Does it cancel with anything at all? It doesn't. So that's not going to be a catalyst, because a catalyst cannot be, well, clearly O3 is present at the end, and I said that a catalyst is not present in the overall reaction. So we see here then that the nitrogen monoxide, NO, is present in the beginning, and it is subsequently present at the end. And because they're on opposite sides of the arrow, they cancel, and they're not present in the overall reaction. So then my catalyst would be the nitrogen monoxide that we see here. So let me restate all that again. So a catalyst is found in the beginning of the reaction and at the end of the reaction, and will cancel out, so it's not found in the overall reaction at the end. An intermediate will be produced as a product in the first reaction and subsequently canceled in the second reaction. And that will be an intermediate. So these are very subtle. They can be confused with each other, which is why I chose to bring this problem up. But I hope that that made a little bit more sense and some insight into how that works. Again, I hope this was helpful, and we'll see you in the next chapter regarding equilibrium.